Right now, the galaxy you are inside is spinning in a way that should be physically impossible. The Milky Way contains somewhere between 200 and 400 billion stars, each one orbiting the galactic center under the influence of gravity, the same gravity that keeps Earth orbiting the Sun, the same force that governs every object in the cosmos. The physics of orbital mechanics are well established, rigorously tested, and do not have exceptions. Under those laws, stars far from the center of a galaxy should orbit more slowly than stars close to it, the same way that planets far from the Sun, Neptune, Uranus, orbit more slowly than planets close to it. The further out you are from the source of gravity, the weaker the pull. The weaker the pull, and the slower your orbit. This is not a theory. This is a mathematical consequence of how gravity works, confirmed across centuries of observation. But the stars at the outer edge of the Milky Way are not moving slowly. They are moving at roughly the same speed as stars near the center. The rotation curve of our galaxy is almost flat, which, according to everything we know about gravity, is impossible. Unless there is vastly more mass in this galaxy than we can see, something invisible, something that does not emit light, does not absorb light, does not interact with anything we have built to detect it, but whose gravity is very much present, holding the stars of the outer Milky Way in orbits they have no right to be in. We call it dark matter. It makes up approximately 85% of all the matter in the universe. It is the most common thing in existence. And we have no idea what it is. This is Deep Space Declassified. New classified file every week. Subscribe before we go further. Let's get into it. The first person to seriously suggest that the universe contained more matter than we could see was not celebrated for it. Fritz Zwicky was a Swiss-American astronomer working at Caltech in the 1930s. He was brilliant, eccentric, and by many accounts difficult to work with. He was also, on this particular question, decades ahead of his time. In 1933, Zwicky was studying the Coma Cluster, a massive collection of hundreds of galaxies bound together by gravity. He measured the velocities of individual galaxies within the cluster, calculating how fast they were moving relative to each other. Then he calculated how much mass the cluster would need to produce the gravitational pull that was keeping those fast-moving galaxies together rather than flying off in all directions. The answer he got was wrong. Not slightly wrong, wrong by a factor of several hundred. The visible matter in the Coma Cluster, all the stars, all the gas, everything that could be seen, was far too little to account for the gravity holding the cluster together. Zwicky concluded that there had to be unseen mass. He called it dunkle materie, dark matter. The scientific community largely ignored him. For 4 decades, the idea sat on the shelf. Astronomy moved on. Dark matter was considered by most researchers to be either an error in Zwicky's calculations or a phenomenon too speculative to take seriously. The universe was what you could see. What you couldn't see was not physics. It was philosophy. Then, in the 1970s, an astronomer named Vera Rubin sat down with a radio telescope, pointed it at a spiral galaxy called Andromeda, and began carefully measuring how fast different parts of that galaxy were rotating. What she found ended the debate and started a new one that has never been resolved. Vera Rubin was not supposed to be doing this work. She had spent years navigating a scientific establishment that was not designed to include her. She was denied access to certain telescopes early in her career. Her initial research was published under her husband's name, at the suggestion of advisors who believed it would be better received that way. She worked methodically and persistently in an environment that presented constant obstacles, and she produced science that eventually could not be ignored. Working with astronomer Kent Ford, Rubin measured the rotation speeds of stars at different distances from the center of Andromeda, and then repeated the measurements across dozens of other spiral galaxies. The pattern was the same everywhere. Near the center of each galaxy, rotation speeds rose as expected. But as you moved outward, instead of falling off, as every law of gravity and orbital mechanics predicted, The rotation curve flattened. Stars at the outer edge of the galaxy were moving at almost the same speed as stars near the core. This was not a measurement error. She had checked. Ford had checked. Other teams had checked. The data was clean. The pattern held across galaxy after galaxy. There was only one explanation that fit. Each galaxy was embedded in a massive halo of invisible matter, a diffuse cloud of something extending far beyond the visible stars, providing additional gravitational mass that pulled on the outer stars and held them in faster orbits than the visible matter alone could explain. Rubin published her findings in 1978. The scientific community could not dismiss them. The evidence was too strong, the pattern too consistent, the methodology too rigorous. Dark matter was real, whatever it was. So what is it? This is where the story becomes genuinely uncomfortable. Because the honest answer, in 2026, is that we do not know. And the reason we do not know is not for lack of trying. Dark matter cannot be seen. It does not emit electromagnetic radiation of any wavelength. No light, no radio waves, no X-rays, no infrared. It does not absorb radiation either. It is gravitationally present. Its mass bends space-time and affects the motion of everything around it, but it appears to be completely transparent to every form of light. This means it is not made of ordinary matter. The atoms and molecules that compose everything you have ever touched, every planet, every star, every gas cloud, every piece of dust in space, are made of particles called baryons, protons and neutrons, the periodic table, all of chemistry. Baryon matter. Dark matter is not baryonic. We know this because there is too much of it. The physics of the early universe, specifically the nuclear reactions that occurred in the first few minutes after the Big Bang, constrained how much baryon matter could have formed. The universe simply could not have produced enough ordinary matter to account for all the gravitational effects we observe. The excess gravity has to come from something else entirely. The leading candidate for decades has been a class of hypothetical particles called WIMPs, weakly interacting massive particles. The theory is elegant. A new type of particle, too heavy to have been detected by previous accelerators, that interacts with ordinary matter only through gravity and the weak nuclear force. Not through electromagnetism, which is why they would be invisible. Not through the strong nuclear force, which is why they would pass through ordinary matter without leaving a trace. The theory predicted WIMPs should occasionally collide with atomic nuclei in ordinary matter. Rarely, but occasionally. And if you built a detector sensitive enough and shielded it from all other sources of interference, you might catch one. So they built the detectors. The experiments that have been built to catch dark matter are among the most extraordinary scientific instruments ever constructed. Deep underground, to shield them from cosmic rays that would otherwise swamp any signal, researchers have placed tanks containing tens or hundreds of tons of ultra-pure material, liquid xenon, germanium crystals. Each detector surrounded by layers of shielding, refrigerated to near absolute zero, monitored by sensors sensitive enough to detect a single photon. The logic is straightforward. If a WIMP collides with a xenon nucleus, it will produce a tiny flash of light and a small electrical signal. Catch that signal, and you have found dark matter. The Lux experiment, deep in a mine in South Dakota. The Xenon experiment, deep beneath the Gran Sasso mountain in Italy. The Pandax experiment in China. LZ, the successor to Lux, now the most sensitive dark matter detector ever built. They have been running. They have been looking. They have achieved sensitivities far beyond what early theorists believed would be needed to detect WIMPs if they existed. They have found nothing. Not a weak signal. Not a hint. Not an anomaly requiring further investigation. Nothing. The most sensitive instruments ever built for this specific purpose have returned silence on a scale that, for the WIMP hypothesis, is beginning to look like exclusion rather than absence of evidence. The Large Hadron Collider at CERN, the largest and most powerful particle accelerator in history, was partly expected to produce dark matter particles through high-energy collisions. It has run for over a decade at energies previously untested. It has made significant discoveries. It has not produced dark matter, 85% of the universe, and we have not detected a single particle of it. There is one observation that makes it very difficult to argue that dark matter simply does not exist. In 2006, astronomers studied a system called the Bullet Cluster, two galaxy clusters that had collided and passed through each other at tremendous speed. When galaxy clusters collide, the ordinary matter in them, mostly hot gas, which accounts for the majority of visible mass, slows down due to electromagnetic interactions, like two clouds of smoke colliding and mixing. But the galaxies themselves, far more sparsely distributed, pass through each other relatively unimpeded. What should happen to the dark matter, if it exists? It should behave like the galaxies, passing through the collision without interacting, because dark matter does not interact through electromagnetism. It should end up in a different location from the hot gas, which got slowed down. Astronomers used gravitational lensing to map where the mass in the bullet cluster was concentrated. Because mass bends light, a precise measurement of how background light was distorted revealed where the gravity was strongest. And the gravity was not centered on the hot gas, where most of the visible mass was concentrated. It was offset, centered in two regions that corresponded to where the galaxies had passed through, and where dark matter, if it were real, would now be located. The mass was not where the visible matter was. It was where the dark matter should be. The bullet cluster is considered the strongest direct evidence that dark matter is not a failure of our understanding of gravity. It is a physical substance, real, present, and separated from ordinary matter by the collision that simply does not interact with light in any way we can measure. But here is the alternative that some physicists refuse to abandon. What if dark matter does not exist? What if what Vera Rubin saw was not the effect of invisible mass, but a signal that our understanding of gravity is incomplete? This is the position of a theory called MOND, Modified Newtonian Dynamics. Proposed in 1983 by physicist Mordechai Milgrom, MOND suggests that at very low accelerations, the regime relevant to the outer edges of galaxies, gravity does not fall off quite the way Newton's and Einstein's equations describe. If gravity behaves slightly differently at those scales, the flat rotation curves of galaxies can be explained without any dark matter at all. MOND has genuine successes. It accurately predicts the rotation curves of many individual galaxies. It produces a relationship between visible matter and rotation speed that has been confirmed observationally across dozens of galaxy types, a relationship that dark matter models have difficulty naturally reproducing. But MOND has a serious problem: the bullet cluster. If there is no dark matter and gravity is simply behaving differently, the gravitational mass of the bullet cluster should follow the ordinary matter, the hot gas. It does not. The mass distribution in the bullet cluster is very difficult to explain without invoking a substance that behaves the way dark matter should behave. Neither explanation is complete. Dark matter exists but cannot be detected. Or gravity behaves differently at large scales but cannot fully explain cluster collisions. Both possibilities are uncomfortable. And the scientific community is genuinely divided in a way that, on a question of this magnitude, is itself extraordinary. Zoom out far enough from the dark matter debate, and something comes into focus that puts the whole question in a different light. The large-scale structure of the universe, the way galaxies are distributed across cosmic scales, matches the predictions of dark matter models remarkably well. Galaxies do not float randomly through the universe. They are organized into an enormous web, clusters of thousands of galaxies, connected by filaments, with vast empty voids between them. The cosmic web. Computer simulations that include dark matter reproduce this structure with extraordinary accuracy. The same simulations run without dark matter produce a universe that looks completely wrong. Galaxies distributed too uniformly, no filamentary structure, no clusters, no voids of the right scale. When you run the physics of the early universe forward in time, with dark matter included, the universe that emerges looks like the one we live in. Without it, it does not. Dark matter provided the gravitational scaffolding for everything. In the early universe, before ordinary matter could even form atoms, dark matter was already clumping under gravity, forming invisible halos that would later act as seeds for galaxy formation. Ordinary matter, the stuff you and everything you have ever seen is made of, fell into those dark matter halos and assembled itself into stars and galaxies because the framework was already there. We are, in a very literal sense, the minority. 15% of the matter in the universe is the kind we are made of. The kind we can see, touch, and measure. The other 85% is something else, something older, something that was there first and built the scaffolding that everything else grew on. And we cannot identify a single particle of it. Here is the question that makes this more than a physics problem. If dark matter exists, and the evidence says it does, then the universe is far stranger than our best science has accounted for. The matter we have studied, the particles we have accelerated, the detectors we have built, the models we have constructed, over a century of particle physics and cosmology, all of it has been describing 15% of reality. The other 85% has been present in every observation we have ever made, shaping everything we have ever seen without ever being identified or characterized. Every time you look at the night sky, you are looking at a universe that is mostly something we cannot name. Every galaxy you see is embedded in a dark matter halo, many times larger than the visible galaxy itself. The space between galaxies is threaded with dark matter filaments. The motion of every star in every galaxy is influenced by the gravity of something we have never detected. And if we are wrong about dark matter, if MOND or some other modified gravity theory turns out to be correct, then Einstein's general relativity, the most tested and confirmed theory in the history of physics, breaks down at galactic scales, which would be equally extraordinary. Which would require an equally fundamental revision of what we understand about the universe. Either dark matter is real and we cannot find it, or gravity is not what we think it is. One of those has to be true. Neither of them has been resolved. Future experiments may provide an answer, or they may deepen the mystery. The LZ experiment, the most sensitive dark matter detector ever built, is currently running. It is looking for WIMPs at sensitivities that cover almost the entire theoretically predicted parameter space. If WIMPs exist in the mass range theory predicts, LZ should see them, or rule them out definitively. Other searches are focused on axions, a different hypothetical dark matter candidate, much lighter than WIMPs, proposed originally for a different reason in particle physics and later recognized as a potential dark matter explanation. The ADMX experiment in Washington state has been hunting axions for years. Others are following. The Euclid Space Telescope, launched in 2023, is mapping the distribution of galaxies across the universe with unprecedented precision, trying to pin down the properties of dark matter through its gravitational effects on large-scale structure rather than through direct detection. The Vera Rubin Observatory in Chile, named after the astronomer whose rotation curve work established dark matter's existence, will survey the entire southern sky repeatedly, looking for the subtle distortions in galaxy shapes caused by dark matter's gravitational lensing. All of this is real science in progress. All of it is still ongoing. None of it has produced a confirmed dark matter detection. The thing that holds the Milky Way together, that shaped the cosmic web, that constitutes 85% of all the matter in the universe, remains unknown, remains undetected, remains one of the deepest unsolved problems in the history of science. Think about what it means to live in a universe that is mostly invisible. Everything you have ever seen, Every star, every planet, every galaxy, every nebula, every photograph taken by every telescope ever pointed at the sky represents 15% of what is actually there. The dominant component of the cosmos is something we have no direct evidence for, no identified particle for, no confirmed detection of in 90 years of looking. Vera Rubin understood this better than most. She spent decades making precise, careful measurements that revealed the presence of something that should not have been there, in galaxy after galaxy, without a single exception. Late in her career, she noted that her work had raised far more questions than it answered, which she considered entirely appropriate, because the universe was under no obligation to be simple. We are made of the minority. Our bodies, our planet, our sun, our galaxy, everything we have ever interacted with, everything that has ever affected us, is constructed from 15% of what exists. The rest is dark, invisible, present in every direction you point a telescope, shaping the structure of everything you see without ever being seen itself. We do not know what it is. We do not know if we will find it in the next decade or the next century. We do not know if our detectors are simply not sensitive enough, or if the particles we are looking for do not exist. What we know is this: the galaxy is spinning in a way that requires it. And it has been spinning that way for billions of years, held together by something we cannot name. What do you think dark matter is? WIMPs, axions, a modified theory of gravity, or something we have not even imagined yet? Tell us in the comments. And subscribe for the next classified file, because the search for the most common thing in the universe is still very much ongoing.